All right, let's talk about sorting. It's one of those things that's just fundamental in computer science. But have you ever really stopped to think about how you tell a machine to put things in order? In this explainer, we're going to meet some of the classic algorithms, the ones every programmer really ought to know. And then we'll meet a really interesting specialist that kind of plays by its own rules. So let's get into it.
First things first, let's start with a really simple question. Imagine I hand you a totally shuffled deck of cards. How would you sort it? Seriously, think about it for a sec. Maybe you'd spread them out, find the ace, then the 2, then the 3, or maybe you just pick up the cards one by one and slide them into the right spot in your other hand. You probably do it without even thinking, right? Okay, hold on to that thought.
Because that is the real puzzle. A computer doesn't have our intuition. It doesn't have hands or eyes. It needs a super precise step-by-step, no room for error set of instructions. And that, my friends, is exactly what an algorithm is. So let's look at a few different ways we can give the computer those instructions. Okay, let's dive in and meet our first contestant. This is selection sort, and I like to call this one the perfectionist picker. And trust me, it lives up to the name. This algorithm absolutely, positively has to be sure it has the perfect choice before it does a single thing.
The whole idea here is pretty simple, but it is so meticulous. The perfectionist picker will scan the entire messy, unsorted list, find the absolute, undeniable smallest number in the whole group, and only then, with total confidence, will it place it at the very beginning of the sorted section. It's patient, it's thorough, and it leaves absolutely nothing to chance.
So here's what that looks like in action. On the very first pass, it scans the whole list, finds the smallest number, and swaps it into the first position. Boom, that first spot is now sorted and locked in. We don't touch it again. On the second pass, it completely ignores that first spot and finds the smallest number in the rest of the list and swaps that into the second position. It just keeps doing this, shrinking the messy part of the list by one element each time.
And the code? Well, it tells the exact same story. That outer for loop is what moves our sorted boundary along. But the real action, the real perfectionist part, is that inner for loop. That's the search party. It marches through the entire rest of the array just to find one thing, the index of the minimum element, min index. Only after that huge search is over does it finally do a single swap.
So what's the report card for our little perfectionist? Well, all of that careful searching comes at a price. See, selection sort doesn't care if the list is already sorted or if it's pure chaos. It does the exact same amount of work, the same number of comparisons, every single time. That gives it a time complexity of O(n squared, which, to be honest, is pretty slow. But on the bright side, it's efficient with memory. It does all its work in place, giving it a nice O(1) space complexity.
All right, let's move on from the perfectionist and meet a totally different character. Next up is bubble sort, who I call the neighborly swapper. This one isn't about the grand plan. It's all about what's happening right next door.
So instead of this massive list-wide search, bubble sort just looks at 2 numbers at a time, 2 neighbors. If the one on the left is bigger than the one on the right, it just swaps them. That's it. It does this over and over all the way down the list. And with each full pass, the biggest, heaviest, unsorted number bubbles up to its correct spot at the end. It's kind of like a bubble in a glass of soda rising to the top. The process is super straightforward. Compare and swap, take a step, compare and swap, take another step. After you do this for the whole list one time, the biggest number is guaranteed to be at the very end. So you do it again, but this time you can ignore that last element. But here's the really clever part, the secret sauce. If you go through the entire list and you don't have to make a single swap, what does that tell you? It tells you the list is already sorted and you can just stop.
And that one little optimization is what makes this algorithm so cool. You see that swapped variable? It starts as false, and we only flip it to true if we actually make a swap. Then at the very end of the pass, that line right there, if not swapped, break. That is the genius move. It's the algorithm's way of knowing when to call it a day, and it can save a ton of unnecessary work.
And that optimization totally changes its report card. Yeah, in the worst-case scenario, like a list that's sorted in reverse, it's still slow, O of n squared. But what about the best case? A list that's already sorted. Well, it makes one pass, realizes no swaps are needed, and stops. That gives it an amazing best-case time of O of n. It's simple, yeah, but it's surprisingly smart when the data is almost in the right order.
Our third classic algorithm is probably the one that feels the most, well, human. Let's meet insertion sort, or as I like to call it, the savvy card player. Because this is almost certainly how you sort a hand of cards without even realizing it.
The logic here is just so intuitive. You basically imagine your array is in 2 parts,
a sorted part on the left, which is your hand, and an unsorted part on the right, which is the deck. You start with just one card in your hand. Then you pick up the next card from the deck and you just insert it into its correct spot in your hand, shifting the other cards over to make room.
So you pick up your new card. You look at your sorted hand, starting from the card on the far right. Is my new card smaller? Yep. Okay, shift that one over. Is it smaller than the next one? Yep. Shift that one over too. You just keep shifting cards to the right until you find the perfect spot, and then you just slide your new card right into the gap you've made. It's a smooth little shuffle and insert move.
And the code reflects that action perfectly. We hang on to the value of our current card, then that while loop is where the magic happens. As long as we're looking at a card in our hand that's bigger than our new one, we shift it to the right. As soon as that loop stops, we've found our gap, and that last line, RRJ plus 1 equals current, slides our card right in. It's really elegant when you see it.
Now, when we look at its report card, it might seem a little familiar. It's a lot like bubble sort, actually. Worst case, still O of n squared. But if the list is already sorted, it's super fast. It just looks at each element once, sees it doesn't need to shift anything, and moves on, giving it a fantastic best case of O of n. It's really, really good for small lists or lists that are already mostly sorted.
All right, we've met the classic crew. They all compare numbers to sort them. Now it's time to meet the specialist, the one that throws the rulebook out the window. This is counting sort, and you can think of it as the accountant.
Okay, this is the most important thing to understand. Selection, bubble, and insertion sort all work by comparing two elements. Is A bigger than B? Should we swap them? The accountant doesn't care about any of that. It never, and I mean never, compares two numbers from the original list against each other. Instead, it just counts how many of each number it has.
Think of it exactly like taking inventory. First, the accountant finds the biggest number on the list just to know how big its ledger needs to be. Then it creates a brand new count array. It goes through the original list and just makes tally marks. Okay, I see 3 5s. Check. 2 8s. Check. 1 2. Check. Finally, it just rebuilds the sorted list by reading from its ledger. Okay, I had 1 2, so I'll write down a 2. I had 3 5s, so I'll write down 5 5 5. It's incredibly fast, but, and this is a big but, it only really works well for whole numbers inside a pretty small range.
And that gives us a very different looking report card. Its time complexity is O of n plus k. Now, n is the number of things we're sorting, and k is the range of the numbers. So if k is small, this thing is ridiculously fast, way faster than O of n squared. But the trade-off is space. It needs that extra ledger array, and the size of that ledger is k, so its space complexity is O of k.
Okay, we've met the perfectionist picker, the neighborly swapper, the savvy card player, and the specialist accountant. That's quite the crew. Let's do a quick pop quiz just to make sure it all stuck. Ready?
Question 1. Which algorithm is the most efficient if the array is already sorted? That would be our optimized bubble sort, clocking in at O of n time. Question 2. If you're using insertion sort on the list 10 2 5, what's the very first main action? You take the 2, shift the 10 over to make a gap, and then you insert the 2 at the beginning. And finally, true or false. Selection sort always performs the same number of comparisons no matter what. That is absolutely true. Its perfectionism means it never, ever takes a shortcut.
And that's a wrap. We've seen 4 totally different ways to bring order to chaos. And each one has its own personality, its own strengths, its own weaknesses. And I think the real lesson here is that in programming, there's very rarely one best way to do something. It always depends. So, I'll leave you with this final thought. If you had to invent your own sorting algorithm, what would its personality be? What crazy trick would it use to get the job done?